Good afternoon, I'm Mr. Ish. Thank you for joining me. In this video, we're looking at a single question. We're evaluating that series with regards to the partial sum, the actual sum, and the error. We'll start here with the actual sum or the true sum of the series. It would look something like how I have written here already for you. When you're looking at this, we should be thinking about an infinite geometric series because that's what it is. If you take each succeeding term and divide it by a preceding term, like 1 over e squared divided by 1 over e, you'll have a common ratio which will be 1 over e. The common ratio here being less than 1 tells you it's a convergent geometric series. Therefore, you can use this. The sum of this series up to infinity, from 0 up to infinity, would be your a1 term divided by 1 minus r, which would be 1 over e to the 0, which is 1 over 1 minus r, which is 1 over e. All you have to do is just that simple computation. You'll have e minus 1 over e, which is going to be e over e minus 1. Your sum of this series, or your actual sum, will be e divided by e minus 1, which would represent the real value. If you do this on the calculator, you end up missing out on too many decimal placeholder values, but you can still attempt it. You're looking here at, let's look at the denominator first. This right here is the value of your denominator, which we can save it. You're taking the numerator and you're dividing it by that. You have 1.581976, which I can put for you right here, 1.581967. That represents a good true value, missing the numbers right there, the digits afterwards, but that right there is the actual value, e divided by e minus 1. So the actual sum, or the sum of this series, has been completed. Now we look at the partial sum. The purpose behind the partial sum is you can do a finite calculation and hope that it would be very close to the actual calculation or the actual sum. And I want to do a finite calculation, the partial sum from n equals 0 up to 4. That would be 5 terms. What will I have? I'll have 1 over e to the 0 plus 1 over e to the 1 plus 1 over e squared plus 1 over e cubed plus 1 over e4. Even though I'm going up to an n value of 4, I have 5 specific terms, 5 total terms. And let's do this computation. We can start from here and go backwards. Place the value over here for you. You can easily do this on your calculator. The value I'm getting here after that computation is 1.571317432, and I'll put it over here. 1.571317432. I can get the good margin of error. If I can minus this from this value or that true value and divide it by that true value, I'll get a margin of error, and I can show that for you, and I'll do it. I have 1.571317432 minus that true, or the sum of series, the actual sum of series, divided by that sum of series times 100. I have minus 0.67379% error. What does this indicate? It means we're underestimated, but that's fine. We're very close. Minus 0.67379% error, underestimated by that amount of error. But that's good. It's very close. Anyhow, we can get another way of doing this error determination using the integral procedure. And you know it would look like this. Limit as t approaches infinity, we have from n up to t. The reason why we put n over here, because then you can use this outcome of this integral procedure for an error determination for as many number of terms as you want. You're looking at a function which is e to the minus x dx. You do the polynomial substitution technique. U is equal to minus x, du is equal to minus dx, dx is equal to minus du. It's a definite integral. You have a u1 which is equal to minus n, and you have a u2 which is equal to minus t. You're suddenly looking at an integral which is like this, minus n minus t e to the u du. You see you have a larger number here and a smaller number here. Technically here was the smaller number, larger number, but by putting a minus, this has become the larger and the smaller. You can hit everything here with a minus and then flip the intervals around. You'll have this. You'll have here a minus t minus n, and then you have e to the u du. And you know, this limit right here is applying to each of these steps. I'm just not writing it out, but that limit t approaching infinity applies here and it applies here. Anyhow, what's the antiderivative here? It's e to the u. Limit as t approaches infinity, we're looking here at minus t minus n. You have e to the minus n minus e to the minus t. This zeroes out because as t approaches infinity, you're looking at 1 over e to the infinity, which is just a 0. Your outcome of this integral procedure, which would give you that factor for error determination, is e to the minus n. Here n represents the number of terms. Don't put this 4, because we went from 0 to 4, it would be incorrect. You would greatly misrepresent your error. You have to do the number of terms. We have 1, 2, 3, 4, 5. Even though we went from 0 to 4, we have 5 terms. Therefore, your error here would be e to the minus 5, and it's 1 over e to the 5, and that would give you your error rate. We can do this here on your calculator. You do 5 and you invoke the exponential and you do the reciprocal. I have 6.737946 times 10 to the minus 3 multiplied by 100 to get the percentage rate. It's 0.67379. 0.67379% error. That's good. It's exactly like this. Here the negative just telling you were underestimated. You're not getting a positive or negative outcome over here simply because you're only getting the actual percent error. This positive or negative here indicates whether you over or you underestimated. That's it. But this here is a good answer. Your sum of your series was good. Your partial sum of the series was good. Your error here is good based on an n value here, the number of terms being 5. You could have put any number of terms over here and then you could have gotten the error rate. The larger the n, like the more terms you do, the smaller this error rate, because then the closer you are to getting towards that true sum of that series. If you have a small n value, a fewer number of terms, you'll have a larger error percentage rate. And that right there brings us to the end of this video. Thank you for watching.